Hello, everyone. So I will talk about the classical turbulent flow in a two-dimensional so-called lead-driven cavity. It's a jargon. I think it's known among the computational fluid dynamics community. And usually this lead-driven cavity is used for a benchmark of new, for example, if you find a new discretization method, and usually you use this lead-driven cavity flow as a benchmark. The pointer. So this is on your left. So this is a stream function with a Reynolds number 10,000. The figure is taken from the textbook, the recent textbook by Ruben and Gajar. And it's nonlinear stationary solution to the Navier-Stokes equation. So the lid, what we call lid, is the top wall, and the top wall is moving to the right. This one? Okay. So the top lid is moving to the right with a constant speed. So this is the canonical setting of the so-called lead-driven cavity flow. And as far as the Reynolds number is small, it produces a nonlinear stationary solution. So typically, you measure, for example, the maximum of this point or maximum of this point. And there are many examples of this calculation. And there are nice tabulated results about, for example, the coordinates of the separation and so on. Then you can compare your result with those tabulated data. So in that sense, this cavity flow is a kind of benchmark. And as far as I know, people do not increase the Reynolds number in this setting. The reason may be coming from this setting. So this lid is moving to the right, but in the corner, it produces some kind of singularity. It's an artificial singularity, but we need to remove them in order to increase the Reynolds number. So this is another kind of practice in the computational fluid mechanics community. So that is called the regularized read motion. So now I have adopted the regularization proposed by Shen. And he proposed the top wall should move in this manner. So in this prescribed velocity of the lid, there is no corner singularity. So with this regularized read, I just calculate stupidly the Navier-Stokes equation with the boundary condition for the lid, and for the other side wall and bottom wall, the velocity is 0. So the boundary condition is no slip, and the equation is just a two-dimensional Navier-Stokes equation. And I have used the standard Chebyshev-Tao method. And so I solve the time evolution, but it reaches stationary state. And so for this particular flow, the Reynolds number is 10,000. So this is a nonlinear stationary solution. And from now on, I increase the Reynolds number. So the Reynolds number is defined in this manner. So U0 is basically the maximum speed of the top lid. And 2L is the length of the square. So the Reynolds number is below 10,000, the flow is stationary, and your Reynolds number is slightly above 10,000, then the flow becomes periodic, like this one. And then it becomes quasi-periodic, and if we increase further, then the flow becomes chaotic, and eventually turbulent. So in the turbulent state, looks like this one. So now the Reynolds number is 256,000. So the left, I showed you the stream function, but for the time dependent flow, the instantaneous streamline doesn't provide you a lot of information. So I showed you the contour of the vorticity. So the top lid is moving to the right, but on the corner they are regularized. So you can see some vortex sheet emanating from the top lid and then move to this direction. And sometimes this sheet becomes unstable, and suddenly it, so sometimes those separated vortex layers becomes unstable, and we end up, we have point vortices or vortex blobs, and those blobs are then going inward, and this is the turbulent state of the 2D lead-driven cavity flow, right? So there are a number of questions we can ask. For example, the number one, so how the dissipation rate? So the dissipation rate of the envisaged conservative quantity is the central in the turbulent theory. So in this case, probably the entropy. The entropy is an implicit invariant in this case, and the entropy is most important quantity. So that means we should focus on the entropy dissipation rate. So maybe the first question is how the entropy dissipation rate behaves as a function of the Reynolds number. So number two is, of course, if this entropy dissipation rate behaves in, let's say, the same as the three-dimensional turbulent flow, then we expect there's some entropy cascade, and what kind of cascade we can observe. And the number three is the standard one. So is there any nice scaling law, for example, the scaling law in the energy spectrum, or the structure function, and so on. And the last question in the list is the mean velocity profile. So usually when we focus on the channel flow or pipe flow, the universal mean velocity profile law is so-called logarithmic law of the wall. So I'm just curious to know if this universal law carries over to this two-dimensional lead-driven cavity flow. So today I focus on the question number one and number four. So the first one, so the entropy dissipation rate. I start with the entropy budget. So the capital Q is the entropy. So the time derivative of entropy behaves like this one. So since this is not a periodic flow, we have surface integral. The surface integral doesn't vanish because of the lid and sidewall and bottom wall. So this O integral is just the surface integral in 1D version. So N is the normal vector to the wall. So the last term is the term we are most familiar. And as I show you in the next slide, so this term actually acts as an entropy input. So here I denote beta in. So the entropy input is can be written here. So this is a entropy input per area. So I divide by the area of the square. So this entropy input is coming from lid and also other wall. So other wall is a side wall and bottom wall. So the last term is the energy dissipation rate, because this is a positive definite. So this is always negative. So this term is really, as I show you in the next slide, this is the entropy dissipation rate. So in a statistically steady state, if such a state can be realizable in this setting, so then this dq dt should be 0. So that means the entropy input coming from the lid or sidewall or bottom wall is basically equal to the dissipation. So let's look at the numerical data. So on the left, so the top graph is entropy dissipation rate, beta. So the second one is entropy input from the top lid. So this is positive, but not equal. So there are some tiny difference. The tiny difference is actually coming from the entropy input from the side wall or the bottom wall. So if we add this beta in lead and beta in other wall, the sum is this beta in. The sum is basically equal to the dissipation rate. So this is time, and this is the input. The orange is the input. So the blue is the dissipation rate. So now this input and dissipation rate is basically equal. So we have statistically steady state. Okay, so then as I told you, this term is the legal entropy dissipation rate. And if I take the time average of this entropy dissipation rate for a certain long time, and then I plot those time averaged entropy dissipation rate as a function of Reynolds number. So this is the result. So this is a log-log plot. So the entropy dissipation rate, time averaged, goes like Reynolds to the 1/2. So as I discussed, the Reynolds number below 10,000, so this is basically the stationary state. So this is the laminar state. And above 10,000, it's periodic. And then here is the turbulent state. So both the stationary and turbulent state has the same scaling, but it seems to persist for a much larger Reynolds number. That's okay, so we don't know. I just calculated up to 500,000. Okay, so I showed you the time average, the entropy dissipation rate as a function of Reynolds number. So the Reynolds number is defined in this manner, and it grows as we increase the Reynolds number. So this situation is very different from the three-dimensional turbulence. In three-dimensional turbulence, as we know, there's something called dissipative anomaly. So the dissipative anomaly means that the energy dissipation rate becomes constant as we increase the Reynolds number to infinity. So this constant doesn't depend on the kinematic viscosity. So that is probably the most prominent feature of the three-dimensional turbulence. So if we compare this scaling with this one, so it's very different. Okay, so we have this numerical data. So beta is proportional to the Reynolds 1/2. So now I offer you a consistency argument. So assume our vorticity has some dominant structure. The dominant structure is capital omega. The capital omega can be written as u over delta. So u is some characteristic velocity. Delta is some length scale associated with the dominant vorticity. So the dominant vorticity, yeah, here's an assumption, and it's taken from the textbook. So we know the boundary layer thickness goes like kinematic viscosity to the power 1/2. So we plug this expression to the entropy dissipation rate. So this gradient of omega is just the omega, capital omega divided by the delta squared. And now we assume the dominant vortical structure here is sheet-like. So sheet-like means the longer extent is capital L. Capital S is basically the system size. So delta is the small thickness of the layer. So this area is delta times capital L. So your entropy dissipation rate can be represented in this manner, and then just calculate with this assumption, and that gives you beta behaves like this one, and this one just gives you the Reynolds to the 1/2. So the important question, of course, is does this scaling persist as the Reynolds tend to infinity? At that we don't know, but as far as the numerical data suggests, this scaling probably persists, and that means the entropy dissipation rate diverges weakly. Okay. So this is the Reynolds 1/2 we talked about, but we can measure higher order moments. So I took the variance, so it's a squared beta. So the variance of the entropy dissipation rate behaves like Reynolds to the Reynolds squared. So for this one, I don't have a good explanation. But some of you may notice that means beta have some multiscaling property. If we assume multiscaling, then we should have this kind of different exponent. If we have just the single scaling, then this should be Reynolds to the power 1, right? So, but I don't have a good explanation for this scaling. So you are invited to figure it out. Okay. So that was the first part of the talk. So I moved to the so-called mean velocity profile. So this is the instantaneous streamline. So let's consider the vertical line, the central vertical line. And so x is 0, and I take the time average of the velocity along this line. So the horizontal component of the velocity and for the vertical component of the velocity. The dominant part is coming from the horizontal component of the velocity. So I stick to this time averaged horizontal velocity field as a function of y. So this t dependence vanishes. So this mean velocity profile is just a function of y. So the so-called logarithmic law of the wall should take this form. So the u plus is a suitably normalized horizontal velocity component. Y plus is a suitably normalized the vertical component. And this kappa is what is known as a von Neumann constant, which is considered to be universal. It doesn't depend on the pipe or channel or other kind of wall-bounded flow. Okay, so this is the time averaged horizontal component of the velocity field along the central vertical line. So this is the bottom wall. So this is the top lead. The top lead should have the velocity 1. So the curve reaches this point. And for the bottom wall, so the y equal -1 is the bottom wall. So the bottom wall, the velocity is 0. So the beam velocity profile is this one. So as we increase the Reynolds number from 64,000 to 256,000, as you can see, this maximum goes to right. So that means the velocity is becoming more and more vertically flat. So this is the typical behavior for the wall-bounded high Reynolds number flow. So then I thought maybe here we should have some universal velocity, mean velocity profile, which is reminiscent of logarithmic law of the wall. So to observe this, we need to rescale the velocity and the coordinates in a suitable manner. So the logarithmic law of the wall takes this form. So B is a constant, the kappa is a universal constant, B is less universal constant, and the scaling is this way, is taken this manner. So u tau is a so-called friction velocity. The friction velocity is defined in this way. So this, the things in the parentheses is basically the viscous stress at the wall. So the viscous stress gives you the friction velocity, and from this friction velocity, we can define the length scale. So we use this u tau and L tau as a scaling variable, then we have this universal velocity profile. So I calculate those U tau and L tau in the cavity flow and normalize it. So this is a result. So this is for the smallest Reynolds number. So this blue is the highest. So for some particular Reynolds number, it happens to be very close to the so-called logarithmic law of the wall. So this one. So this orange line is the logarithmic law of the wall. So that's kappa 0.4 and B5 is the well-documented universal profile. But if we change the Reynolds number, it seems the log regime, there may be some log regime, but the constant in front may be different from the universal profile. But for this, it's an ongoing work, so I have not yet reached the definite conclusion. Okay, so this is another profile along the central horizontal line. So this is the central horizontal line. The coordinate is x from -1 to 1. So this is the left wall. This is the right wall. So as you can remember, as you see, if you remember well, so the lead is moving right. So the moving right lead makes some vortex sheet to the right. So the reminiscent of the vortex sheet appearing in this manner. So it has some very sharp turn. But for this left velocity profile, again, this shape and this behavior as a function of Reynolds number is very similar to the low-bounded high Reynolds number turbulent flow. So let me focus in this region and take the standard way of normalizing this time is V plus and in this time the X plus. So the X plus and the V plus, divided by V tau gives you the V plus. So the data looks like this one. So again, so this viscous part collapses very well, but in the region where we expect the log law, the variations is very large. But if I insist, then there may be some tiny region where log behavior may exist. But definitely there are other straight region, or maybe which may not be the log region at all. But this is what we observe for the central horizontal line on the around the left wall. Okay. So this is the end of my talk. So I talked about the entropy dissipation rate and mean velocity profile. Thank you.
I'm just curious with regards to the scaling. So you R to the half for beta and R squared for the variance. So yeah. Normally the envisaged 2D Navier-Stokes have these additional invariants, the Casimirs, higher order moments, essentially, of the vorticity. Mm-hmm. So I'm just wondering if you try to extend your analysis for the fourth order moment, whether it might shed some information about the RE squared scaling.
Okay, so yeah, actually, yeah, it's a very good question, and I agree with your point. But it seems the distribution of beta looks probably a power law type, and higher order moment is likely to diverge. But of course, for the finite range of the simulation, it is a power law type distribution, but truncated. So if we just look at the higher and higher order moments, those moments are probably affected by the truncated part. So yeah.
So you have to be careful how to interpret it, yeah.
Right,
yeah.
But I think for the ideal scenario is that the dissipation rate, distribution of the dissipation rate is a power law type. And that gives you this kind of scaling.